Hi, it's time for another math easy solution. Today we're going to discuss further into conic sections and polar coordinates, and now look at variations in the polar equations theorem, which I covered in my last video, but I'm just going to go over the variations in more detail. So first off, recall from my earlier video on the quote unified theorem of conic sections and its simple formulation in terms of polar coordinates. So here is the theorem first off. Recall this one. I'm going to prove this one in a later video or videos, so stay tuned for that. But here I'm going to go over the polar equation form of the theorem and then go over it in a bit more detail. So theorem over here, let F be a fixed point called the focus and L be a fixed line called the directrix in a plane, and then let E be a fixed positive number called the eccentricity, and this set of all points P in the plane such that now you have over here the distance from P to F, so the point that is going to be the set of all points P right here on a plane, and then distance from that point or those points to the focus right here, to the point focus, the distance of that divided by that the distance from the point or points to L, which is the fixed line or the directrix, is equal to E. So the ratio of the distance to the focus and divided by the distance to the directrix is equal to E, the eccentricity. So that is the ratio of the distance here from F to the distance from L is the constant E. So if it's constant, then it's a conic section, which I'll prove in a later video. So the conic is an ellipse if E is less than 1, and it's a parabola if E equals 1, and it's a hyperbola if E is greater than 1. So MES, note the eccentricity is always positive since it is just a ratio of the distances, and distances are taken as just the absolute value. So they are always positive. And I will prove this theorem in a later video or videos, in later videos. So stay tuned for that. And then again, as I illustrated in my last video, it would look something like this. So if this is a set of all points P over here, and this is a specific point P over there, the distance from here to this line called the directrix, divided by, it's at the bottom. So that's a distance from there to there, and here's a distance from that point all the way to the focus, F. So then when you divide it out, you get a constant. So the ratio of this distance divided by this distance is constant E, like that. And this is in fact the conic section, which I will prove in later videos for the parabola, ellipse, and the hyperbola. And now here is the theorem, which I also covered in my earlier video. Well, I just summarized it. Theorem in terms of a simple polar equation. So a polar equation of the form R equals E times D divided by 1 plus or minus E cos theta. Or in this case, or you could also write it as R equals E D divided by 1 plus or minus E sine theta. And basically this is the distance, this D is the distance to the directrix if this is at the origin. So this represents a conic section with eccentricity E and the focus at the origin, and this is in polar equations. So the conic is an ellipse if E is less than 1, and a parabola if E equals 1, or a hyperbola if E is greater than 1. So this is that same theorem above here, but in polar equations, and as you can see, is just a simple formula, and it's variations of the formula depending on how you set up or how the conic section is set up. So the following figures illustrate the different polar equations for various conics. So here, if the x equals to d line, the directrix is over at this point. We have r equals ed divided by 1 plus e cos theta. And there's again, this is at the origin. Remember, it's always at the origin. Over there, the focus for this polar equations to be as above. And then if it's negative d, we have 1 minus e cos theta. If this directrix is over there. And then if the directrix is on the top, then y equals the d, then we have the sine theta as opposed to cosine. And then if it's at the y equals negative d, we have this 1 minus e sine theta. So in this particular video, I will expand on each of the above cases, just to show how the formulas all change. So let's look at the case one. The directrix is at x equals to d, so it looks something like this over there. So let's just draw this manually instead. So let's say we have x equals to, there's the x and y, so x equals to d is this directrix like this, and this is our x equals to d, and this is our L line right there, and this is again our directrix like that. It's a directrix, or you could call it L or whatnot, and there's the focus. It's going to be at the origin, and then it's going to have conics. It's going to look something like this. And then this is the set of all points P, but let's say we have a specific point here, and this one is going to be P. But let's say this point has polar coordinates R and theta, as well as the Cartesian X and Y, like that. Yeah, just for reference, like that. And then basically in Cartesian or on polar coordinates, this means that at the origin right here is the pole. So this is going to be the ray R, and then you rotate by theta like that. So then it has r distance from the origin, and then it has theta angle from the polar axis, which is over here. I'll just write this over here. This is the polar axis, the positive x axis, polar axis. So again, make sure to watch my earlier videos on polar coordinates. I'll put the link in the description below, as well as my last video on conic sections in polar coordinates. Yeah, so we have this. I'm just going to write this a bit closer. And now if we were to draw this downwards like that, this is just the y component, or the y coordinate of it, and there's the x is the horizontal distance across there. And also recall that this is just using trigonometry. This definition of trigonometry you're going to have, and move things around, this is going to be r cosine theta. And now what we'll do is apply the above theorem, this one right here. So we need the set of all points P in a plane such as this ratio over there, so P over PF divided by PL. So that means a distance from P to F, I'm going to draw this across like this distance across here, I'll just move this around here. This is going to be something like this distance is going to be PF like that, and then this distance across here is going to be our PL like that. And in this case, we know what PF is. That's just R. And then this distance across, well, we know this distance from here to here is all the way to D, like that. This is just D there. So that means this distance from here, because we know this one X is at this point. So that means from, let's draw this all the way down like this. This distance across is our PL. This is just going to be, well, D minus this X, which is R cosine theta. Yeah, so thus what we have is thus the ratio PF over PL, the distances, is going to be equal to our E. That's basically part of the theorem. And then the PF is just R. That's just the ray over there. That's just R in polar coordinates. Divide this by, well, this distance, D minus R cosine theta. Because remember, this entire thing is all the way to D. Like this is D. D, subtract this by over here, which is our x, equals r cosine theta. Alright, so now getting back over here, so what we could do now is we can just move this inside here, multiply it out, so we get, well, an E, then ED minus r cosine theta, and then bracket, this equals r, just expand this all out, this equals to ED minus ER cosine theta, like that. And now what we could do is move this over to here and factor out the R, so we get an R, and then we have, well, R factors out, we get a 1 plus E cosine theta, because we subtracted here, so we move it to be positive. This equals ED on this side. And now what we could do is, well, just divide this all out. So we get R equals to ED over 1 plus E cosine theta. Circle this, and we yeah, then there it is. That's our polar equation from the above theorem. It gets it when the directrix is x equals to d, and that's this one right here. So that's a check mark for us, like that. Now let's look at part B, which is when the directrix is the negative side, and see what we have. Yeah, so now let's just do this for this side. So case B, the directrix is at x equals negative d, so then it's going to look something like this. I'm just going to move this graph over to this way, like this. Actually, just draw it more in the center. So this is our x, this is our y, and this is our x equals to d, a line like this, x equals to negative d. And again, this is just our L as well, our directrix, or L. And then this distance here is negative d, like that. And now what we have is this focus like this. This is our F. I'll write this actually above here. That's our F. And it's going to look something like this. The conic, let's just draw it out like that. And now for consistency, I'm just going to draw the point. It's going to be somewhere around here as well on the positive side. P, this is going to be this point right here is PR theta, and the Cartesian is just, again, for reference, PX, Y. Alright, just fix up the graph a bit. So now what we have is the ray is going to be like this. That's our R. This angle is our theta, like that. And then again, we have this top part, that's our Y. This part here is our X, equals to R. The X is distance from here to here. This is R cosine theta using trigonometry. Yeah, so we know that this distance is this is just a distance like that. X equals R cosine theta. R cosine theta. So this distance across here to here is just our D, just the absolute value of the distance, just D. And then we have all the way to this point. This is our PL, because this is the line L across here, and this equals to just going to be D plus R cosine theta, like that, or equals to X, like that. And then this distance is just this is just our right here, PF, like that. From distance from P to F is just equal to R, like that. Yeah, so likewise as above, we can just write now the ratio. Let's write thus. So the ratio now is going to be PF over PL. This equals to E. So PF is just R. It's just always is going to be R in polar coordinates. When the pole is the origin right there, where the focus is located. And then PL is going to be D plus R cosine theta, like that. Now what we can do is just move this over, multiply it out, so what we get is an ED plus R cosine, or ER cosine theta equals to R. Move this over to this side and factor out the R, so what we get is an R, 1 minus this one, because we moved it over to the other side, equals to ED. And now what we can do is move this over, and then we have R equals to ED over 1 minus E cosine theta, like that. So times by cosine theta, and there's this formula like that. So that's a formula for a conic section, which again I'll prove that that theorem is in fact for conic sections. And we scroll over for here, we get x equals to negative d there, and this is the exact same formula. Instead of plus, we have a minus for this case, and here's plus or minus, like that. And then for the other side, we could just do it for the positive to show you that it is in fact sine and instead of cosine. It's the exact same thing, but now you're using sine and cosine. Now I'll just do that as well for completion purposes. Yeah, so now let's look at case C. So case C, the directrix is at y equals to d. So in other words, we're going to draw this out like this. This is the x and y axis. So yeah, there's the x and y axis, and then there is y equals to d. This is our L, or our directrix, and this is at y equals to d, and this point is just d across there on the y axis. So the conic's going to look something like this, and now we have this as a focus as well, like that. So again, I'm going to draw the point across on this positive side. This is going to be our P, and this is going to be our R. The coordinates will be R theta equals to the same as in Cartesian x, y. And again, I'm drawing this only on the positive side because it's in fact, if anywhere you go, it's going to be the same formula, but then the x will just be negative and so on. So I'll just derive it all for this on this positive side, but it fits for all of them still. And again, as explained in my last video on conics in polar coordinates, which I did a little recap on polar equations, so make sure to watch that. Yeah, so I'm just going to move this F over here. Yeah, so likewise, let's just draw the polar coordinates on this. It's going to be R. This is going to be our theta. The now distance is the same thing as equals to, well, absolute value PL. That is just a distance from P to F, like that. Yeah, PF, not PL. Yeah, just wrote it up there. So PF like that. And now the distance to this point across here, this distance is going to be, well, you know the total distance is D. Now this distance across here, remember now in this case right here, this is just the y component or the vertical component of this triangle. And again, this is our y point. This equals to in polar coordinates or sine theta, and you can just use trigonometry for that. Sine theta is equal to opposite over hypotenuse, and so on. So it looks like that. So then this distance across is going to be the difference, this minus this one. So we have here is going to be d minus r sine theta, like that. And this is and then this distance right here is equal to the distance from P to L, because that's our L, like that. There's our P, like that. Yeah, so thus what we have now, the ratio for the theorem, PF over PL, this equals to E, and PF is always equal to just R, like that. And then PL is going to be D minus R sine theta. So there's the ratio. And then we can move this across over here and multiply it out. So we get a E D minus ER sine theta. This equals to R. Move this over and factor out the R. So we get R 1 plus E sine theta. Like that equals to E D. Divide this out. We get now R is equal to E D 1 plus E sine theta in polar coordinates. This is the equation of the conic, and again I'll prove the conic theorem in a later video. So it's scrolling back up to it. Yeah, we could see that is just the second or third case right here. So this is case C. This is R equals ED divided by 1 plus E sine theta. And then the other one, it's going to obviously be minus as the same case over there. But let's just do it for completeness sake and for some algebra work. It's pretty interesting stuff. Yeah, so last but not least, we'll have the case D is the directrix is at y equals negative D. So then what we have is something that looks like this. This is the y, this is the x coordinate. So we have a line here L. This is at y equals to negative D. That's this point right here is negative D. We have the focus F like that, and it goes up like this. So yeah, just fix it up and go something like that. And what I'm going to do is I'm going to draw this again in the positive side right here. Just easier to compare with all of them, just to draw the angles. So this is going to be our point P, has polar coordinates r theta, and again for reference this is the same as x, y in Cartesian coordinates. And then now what we have is we draw this out, there's the ray r, and this ray is equal to, again, PF, the distance, PF like that. And then this is the angle theta. And now what we want is, well, we want to get from here all the way to here. We know that this distance from here to here is equal to, so from right angle to it. Yeah, so it's always going to be right angle. This is going to be our D. And now this distance from here all the way to here, this is now, again, the y component of it. Is our y. This equals to r sine theta, just using some trigonometry. And again, now this is going to be the addition. So this distance from here, or I'll just draw it like, where should I draw it? Here. All the way to the bottom there, that's from this point all the way to here. Let's fix this up. See, something like this. This is our D, or I'll just write this is the distance from P to L. This is our PL, and again, this is going to be the addition now. D plus r sine theta, or D plus y for that point, like that. So that's what we have there, like that. Let me just fix that up a bit better. And now we could just, again, just as before, set up our theorem. So thus, applying the theorem, PF, the distance from P to F, divided by distance from P to L is equal to E, which equals to PF is just going to be R. And then PL is just going to be D plus R sine theta. And like before, we're just going to move this over all the way over there, multiply it out. So we get a ED plus ER sine theta like this. And then on the other side it's just going to be r. So we move this over, factor out the r, so we get a r, and then we have 1 minus, now because it's moving over, positive goes to negative there, e sine theta, this equals to the ed there. Divide this out and we get finally, as expected, we get r equals to ed divided by 1 minus e sine theta, like that. Circle it and we are good to go. This is exactly as expected over here, scrolling all the way up to the case D, the graph right here. This is when it's negative d, we have r equals ed divided by 1 minus sine theta. So plus, minus, sine, and sine. This one's cosine, and cosine is plus and minus. Anyways, that is all for today. Hopefully you followed along. I just wanted to show how we can apply or put this exact theorem in polar coordinates, so we get a simple formula of this form, and depending if it's vertical or horizontal, it's going to change from cosine or sine or plus or minus, and so on. So yeah, basically that's much simpler than having multiple different Cartesian, different formulations and theorems or definitions for the conic sections, as in my earlier videos on parabolas, ellipses, and hyperbolas. In later videos I will prove this theorem to show that it is in fact true and it becomes a conic section when e equals less than 1, e equals 1, and e is greater than 1 for these different cases. Anyways, that is all for today. If you learn, like always, you can download these exact notes in the link in the description below, as well as viewing these notes on Steemit. Follow me at MES, and make sure to check out my cool math and science forums and my chat room right there. I'll be uploading it there as well. And yeah, post any cool math or science related stuff you find. Anyways, that's all for today. Thanks for watching, and stay tuned for another math easy solution.